everyone, my name is Melikyan, and today me and my partner Anahit Sahakyan are going to present our capstone project, that is TelPull device. This device converts PET bottles that we use every single day to usable 3D printing filament. First, I want to start with numbers. Based on reports from OECD, only 9% of the waste PET is successfully recycled. Everything else ends up in the landfills. On the other side, one spool of filament costs around 20 to 30 US dollars that is used in our university. TelPull device solves both of these problems simultaneously. Anna, it will continue from here.
This is for our agenda for the day, and at first we're going to begin with the problem which motivated us to choose this project. As we know and as we noticed, the polymer which exists in the PET bottles and also the filament produced is the same, and there is an advantage that people can make filament from plastic bottles. So we decided to take this advantage and use it in our capstone project, and we can see several problems which it solves, and one of which is PET underutilization. In this case, it's for our university, and in campus we can decrease by this a lot of PET waste. Another one is supply dependency, which comes if, for example, we need an extra filament and we have no time for receiving the filament from other suppliers. We can create it by our own resources, and it's really helpful. Another advantage is prototype costs, because sometimes for a prototype, just testing our 3D models, it can cost a lot with PLAs, but this is another way to reduce our costs and to make it efficient. And also CO2 emissions, which is for our PET, recycled PET filament. It exceeds 3 times less CO2, which does for usual PLA, and which is again an environmental good thing for us. Now about project background and objectives.
So at first, our team was supposed to create this device from scratch ourselves. That means mechanical and electronical design. We have submitted our concepts in December about this, and then in mid-February we became aware that a device like this already exists and is made by a student named Ashot Bardasaryan. So after talking with our program chair, Ms. Sahakyan, we came to understand that instead of making the same device twice, we should concentrate on testing the existing prototype, analyze the engineering specifications of it, try to get filament, print with it, understand how it's working. And this is our collaboration. And lastly, create documentation for how to assemble and use this device. As we know, this is the first time that such a collaboration is done between AUA, ARMAT laboratories, and Real School. And we hope that this will be a precedent, and later on such projects will be more and even be better than ours. So this is the project transition and the new goals that we have defined for our project.
As our supply chain completely differs from traditional ones, as our raw materials is inside in our university, at first we need to find our material sourcing, for which we have 2 direct ways. First one is our collecting center, which is our engineering lab. People would just take their plastic bottles and bring it to our lab. And the second one is the direct collection from recycling bins, which are all over in AUA. So this again is a way. If there is no PET bottles in our lab, we can also take account this option too. We also did a survey to understand how people use in AUA plastic bottles, and it turned out that the majority of them throw their PET bottles in AUA. And after we analyzed and saw that per week they throw up to 1 and 2, the majority of them bottles, which is a completely feasible number for our project. And if when we asked them if they bring their bottles to our engineering lab, if they know such project exists, the majority and most of them answered that they would voluntarily bring them, which is again good results for us, and we can see that it can become part of our workflow. Now let's talk about the preparation. We have the bottles, how we should prepare them to make them a filament. There are three staging: cleaning, label remover, and heating. Label removal can be done in three ways. One is by applying heat. The other one is using a hot water or using an acetone.
So, system description, if we're talking about the workflow, the TelPull device has 5 sequential stages. The first one is cutting. After removing the bottom of the bottle manually, a user inserts it into a cutting mechanism that you can see here. It is consisting of 2 bearings. After the first cut is done, the user pulls the strip through these bearings and creates a uniform strip. The next one is painting. This is just ordinary India ink is used. The strip goes through it and then enters the pultrusion stage where it retains the color. The pultrusion stage is one of the main stages where the strip enters 3D printer nozzle where it forms into a cylindrical filament. The nozzle is maintained at 235 Celsius degrees and plus minus 2 degrees of Celsius fluctuations. The next stage is cooling.
Yeah. Cooling is again an important part because in nozzle the temperature is really high, and if we do not cool during after the pulling, we will have deformations which will worse the quality of filament. And of course, after that we have the spooling part, which basically at first we attach it to the gears manually, and then after a stepper motor starts working and the gear starts rotating, the whole process becomes automatic.
And the electronics part is pretty simple. We have a 12-volt power supply that is connected through from a wall outlet. The main control unit is RAMPS 1.6 that is used for control of 3D printers, and it's attached to Arduino Mega 2560. We have the 3D printer E3D nozzle and NTC 100K thermistor that is measuring the temperature. And for the motor that is rotating the gears, we use NEMA 17. And user interface is provided by an LCD. Here you can see the temperature. It is controlled by PID and is maintained at 235 degrees. Here you can see that it's pretty steady, and we have changed the PID coefficients to achieve this result. Otherwise, it was fluctuating quite a lot and worsening the situation with the filament quality.
Even though we knew all the steps how we should do this, we recreated the product to fully understand how it works, and if there are some challenges, we can face them directly and understand the most efficient solutions. And the first challenge we faced was from the bottle preparation side, because the suggested way how we should prepare the bottle and heat the bottle. In the screen you can see how after the heating the bottle decreases in its volume, which can result in dramatic filament diameter change, which is unacceptable. That's why we have created such you can see here bottle caps which use shredder valves and make air injection. By this we pump air. You can see here we pump with 8 psi, after which we add a full pressurized bottle. When we get the full pressurized bottle, we mount it on a screwdriver and start to heat it like simultaneously with the whole surface. And after we do this step, we get a full smooth bottle which which has the full the same wall thickness and is uniform, which is the best practice for filament diameter, which is the most crucial part here. And here you can see the results. Here we have also the strip width, which is another crucial part for filament diameter. And because of different sizes of the bottles, we have the problem of proper positioning. And during the automatic pulling, we have a problem when the diameter, the width decreases. And as a result, that's why we suggest to have a spooling mechanism, which will just we can at first take out the strip manually and collect it to the spooling system, and then use it directly, because in this way we will have more longer and more consistent strip size. And again, here in the video you can see how difficult is spooling part when we remove the filament, because in this case we don't have a place where we can take out the filament directly. So here every time we should take out every spool, which is really time consuming and in some sense dangerous, and because we don't want to take someone's eye if someone is around. That's why we suggest another option which have a part where we can take out it and take out the spooled filament directly from it. I want to make sure that all these suggestions are done based on the research. We included that research also in our CONOPS, where we analyzed different models of such projects and understood the best practices which can be implemented in our project.
Next, after a short period of usage, we have noticed that the gears have been worn out and broke completely. So we decided to use different approaches. First one is printing them with 100% infill, and the second one is printing them by carbon fiber filament. And both of these work pretty fine, and this is what we suggest doing in the future for people who are going to use it. And last problem, I think, is the filament length, that most people use only 0.5 liter bottles, and the length of it, the filament that is produced, is pretty inadequate for most of the 3D printers. So we have talked with the creator of this device and came to a conclusion that we need a splicer that is going to join the different parts of the filament. We have two ways. The first one is manual, where you apply heat by, for instance, a lighter and join the filaments. That is working, but is not far from ideal. And the next one is again improved and developed with the creator of the device together. We're still looking for some parts that we're missing to create it finally. These are volcano nozzles used, and wire is wound on the metallic part. And after a 5-volt via Arduino is applied, we get 300 Celsius degrees where the welding is happening, after which you can take out the filament after the cooling, and it's going to work pretty fine in the printer and not cause any problems. And testing.
Yeah, after we get our filament, we started our testings. You can see here the testings. We can even give it to you to see them. Of course, everything at the beginning was not fine because we tried several ways. At first, we tested the temperatures when they work perfectly, and sometimes we noticed that in several temperatures or speeds, our prints were failed. And here you can see our failed prints. Sometimes we even the printer started to clog, and it was very difficult to solve that problem of printer clogging. So the testings were done a lot to understand the full profile of Creality, which we should use for later usage, and that students can also use them later. And now, even after our testings, you can see that one of the students of mechatronics course used our PET to create his project of mechatronics, which was introduced well enough and satisfied all the needs it should have to. So we can see that it's already in the workflow of our engineering students.
These are some simple specifications of the device that you can see. It's working from the wall outlet, as I have said. Rated power is 30 watts. Filamentary diameter that we get as a result of testings and fail and test results is 1.75 millimeter plus minus 0.15. Operating temperature 235 for the nozzle. And expediency of the product. This is data for 0.5 liter bottles, how much filament we get. We need around 200 bottles to get one spool of a filament, around 7 working days. That means 8 hours in a day to get one spool. And as we have found out, the cafeteria sells around 1,000 bottles per week. That is a pretty feasible number, and we understand that we can get the needed results in the university if we continue to operate in the future. With Tigran Gevorkian, as he has presented his CONOPS, capstone, we have done tensile tests, and as you can see from the graph, although the PET filament is not as strong as the others, it is pretty flexible compared to others. In this case, the most flexible one out of them. The compared ones are PLA, PETG, recycled PET bottle, and carbon fiber filament. And when comparing the cost, this is really impressive because even though we're accounting for the electricity that we're using, it's still much, much cheaper than any kind of filament that is used in our university. And documentation.
After putting it into workflow, we understood that, of course, we need a documentation for this product because we need to understand that we need to make sure that people who are going to use the product will have the full understanding of how to use this device. So that's why we created 3 different manuals. First manual is assembly manual for the people who have the 3D printed parts and the electronic parts. And with this manual, they can use and understand how to create it. We have a user manual for people who are just simply are going to purchase and use this product, and with this they can they can have all the details they need. And of course, a service manual which will guide them how to maintain the product, and if there are some situations, they will find the answers in that document, of course. And after all this, of course, we should have to put this into workflow. And for that, we organized a meeting with ES students with whom we demonstrated the full process of how this device is working. We made it starting from bottle preparations, and some of the prints you saw are printing after that ES workshop. So it was again part of it, and students learned how later, after we graduate, they can use the device, and the device becomes non-diable. And yes, in our future plans, we have a hackathon with ARMAT students. We cannot open the brackets yet because it's yet is in development progress. But it is going to be a competition related to 3D printing, and the winner is going to get one of these devices. And simply, this is another collaboration which is a fully social work, and as we understood, like this is the whole systems engineering process we get through. And there was it. We want to tell a special thanks to our supervisor who was always near and helped us during difficult times. And thank you everyone who participated and had their own impact for our project. It was really fun and interesting to go through these steps. And if you have any questions, we are ready to answer them.
Before starting the questions and answers session, I want to mention that in a way it is not only Engineering Sciences program. It's Artun Albedian who believed in the collaboration, and the first device was funded by their project. We bought this project, and we knew that by disassembling and reverse engineering, we might not get any of the results. So this was a collaboration among ARMA, the real school, and AUA's multiple units, and everything is open source. And we are going to run multiple sessions, and hopefully we will replace if Armand agrees and confirms, we will replace our filament usage with this device, with the improved one, and hopefully we will get more capstones, green capstones. And I did promise Arjun that we will publish the social impact of the of the device. And from our budget, Engineering Sciences budget, we produced the second version of the device, which will be the gift to the winner of the hackathon.
Great work, and kudos for the user's guide.
Impressive.
Yeah.
Impressive after work, because a lot of times the engineering is good, the documentation is very weak. No documentation matches the high quality of your work. Very well done. I have a couple of questions about the economic feasibility, because the environmental impact we all understand, the waste reduction and waste recycling we all understand. Have you done any calculations about what would be the cost of running of the device and compared to commercial prices for the filament?
Yes, so taking into account the rates of electricity that is used in Armenia, from one bottle we get, for one spool we get around 120 drums AMD.
Only.
Yeah.
for electricity use, and the bottles are basically free if they are bring to us, and if they are not, like the money compared to other filament costs is really much cheaper. And for one bottle need only $2 maximum. But it's not even $2. It depends on the bottle people bring.
100 drums per bottle.
Yes.
No, per spool. And spool, for the spool we use around 40 bottles for one spool.
The numbers don't much, sorry. Because you are saying
200.
200 bottles.
every spool will go for 7 days, 8 hours of working. That would be your device would be consuming less than 10 watt of power. Is it true or not?
We did the testing.
It is consuming 30 watts.
It is consuming 30 watts, yeah. And we did the calculation by that the number of how much does it cost the watt.
It is eating, pulling, cutting, cooling, spooling, everything all together.
Yes.
30 watts.
Yes.
Yeah. In average, it's average number.
Yeah. Yes.
What will be the sustainable price for one spool to provide to the market?
So we have made these calculations and everything based on the assumption that it's going to be used by students in the AUA or RMAT. So it's not going to be commercial product
from
for selling.
our side. But it was commercial from the Arshot side, as we know, and we know that he brought it with 30 and 20,000 drums.
No, the whole device.
The whole device, yeah.
You guys should convert this into a vending machine.
It's an idea we can.
Yeah, we had
later
that
on.
idea at first, how to collect the bottles. Yes.
Okay, I have a question and a comment. First, congratulations, really impressive after work, as we mentioned. My question is, what future work would you recommend for other students? And then one comment on the cost. Of course, I mean, in the commercial setting, you would apply a lot of labor costs.
Yes.
And this is why it is so incomparable to market prices for the filament. But I think it's a good idea to think of the commercialize and your volumes. For your reference, we have, or everyone's reference, we produce only from beverage bottles, meaning these bottles. We produce 12,000 tons of PET waste yearly. 12,000 tons.
Yes.
Which converts into 400 million bottles. Okay?
About yes.
So just think about that number and scale it up your project. And by the way, we export these bottles, these materials to Russia because we cannot recycle it domestically. So if that's a marketable, if your filament is really marketable, we have a solution. We have a serious, real solution for this.
Yes.
But the future work for the engineer.
The future work, we're still in contact with with the developer of the device, and we're working on a version 2 that is going to be much better and much more efficient. It will be much easier for students to use, etc. And after it, when we have the hackathon and when we have workshops for engineering students, and when we distribute the manuals for them, I think it's going to be easier to continue manipulating these devices later on.
And in general, any ideas from your experience, from your lessons from this device? Any ideas of automation, like going completely automated? Like you could bottle just as it mentions that vending machine, meaning you just put the bottle and it goes.
Yeah.
Any feasible automation options?
When we
This requires a lot of things,
Yes.
manual.
Yes.
when we compare the cost and benefit with each other, we came to a conclusion that in this scale, at least for now, it's better to have the manual than No, I mean in the university. Yeah. But when it's industrialized, I guess, and that's the case when we can think
So-
about fully automating everything.
For industrialization, for being industrialized, we have to have a big factories, and it's like completely different thing.
I think it will be a very strong addition to your, research and work practice, maybe for future work even. It's just the demand. I would be very interested to hear the market demand for filament in Armenia. How much filament is really demanded right now for that? So the potential for your conversation. But great job.
Thank you.